What up, pre-calculus students? Coming at you early in the morning. Got a little sun situation going on here. It's one of those soccer games, tennis matches. Anyways, we need a graphing calculator for this. I got my graphing calculator out. If you don't have a graphing calculator, you could still do these homework problems using Desmos, but for in class for the quiz, you need a graphing calculator. We have to know how to use this graphing calculator for the AP calculus test. So what do we have to learn how to do with the graphing calculator? Find maxes, find mins, find zeros, make sure we can see all of the relevant portions of the graph. So we're going to go into y equals a lot. We're going to be graphing a lot. We got x cubed minus 3x squared plus 3. Oops, that always happens. You got to go to the right. We were told there's a point of inflection at 1. That's nice. Looks like I can see everything. I kind of know what an x cubed looks like. It kind of looks like that. So I kind of can see everything. Questions are determined when f is greater than 0. So that's when the function is positive versus f is less than 0. We need to be able to find the zeros to answer this question. There are two ways to find zeros. My favorite way is to graph y equals 0 and find intersections. Now, just to show you that I'm graphing y equals 0, I'm making this line a little bit more solid. So you can see there's the line y equals 0. You can second calc find the intersection of your cubic and your y equals 0. So that's, again, second calc intersect, number 5. And then go over to the intersection you wish to find. Press enter, enter, enter. And we get negative 0.879. We want to have answers rounded to the third decimal place or truncated to the third decimal place. I like to truncate, which just means write down the first 3 numbers and then leave the rest off. So we are negative from negative infinity until negative 0.879. We're going to be positive from negative 0.879 to 1.347. We are above the x-axis there. Let me show you the other way to find zeros. Let's say you forgot to graph y equals 0. You can use the second calc 0 function. Second calc 0, number 2. Locate your 0 that you want to find. Go to the left of it to create a left bound. You see that arrow will point towards the 0 you're trying to find. Go to the right of the 0, creating a right bound. Your calculator will do a arithmetic process, numerical process to find that 0, 2.532. So from the 1.347 to 2.532, we're going to be negative. And then we are positive after that from 2.532. Oops. 2.532. 2.532 all the way to infinity. Cool. We are told there's a point of inflection at 1, so that's kind of important to know. If you want to find like the locations of these points, you can always press the button trace. What I don't like using trace is not like clicking left and right, but rather like finding an x coordinate 1 and boom, like you find the y coordinate that's associated with that x coordinate. It's an easy way to create a table without using table. Easy way to find any point. Okay. Find when the rate of change of f is positive and where the rate of change of f is negative. Okay, so we got to remember how to like translate this question into something that is easy to understand. Rate of change, slopes. Slopes are f are positive. Let's see if I can get this right. Slopes of f are positive when f is increasing. We need to figure out when f is increasing. When is the rate of change of f negative? Slopes of f are negative when f is decreasing. This is why we spend so much time doing those statements on day one, like on average, the function is increasing, or on average, the function is decreasing. Okay, so slopes negative, f is decreasing. We translate the question. Now, we have to find some information. We'll have to find the location of the max and the min here. Maxes and mins will be where we change from increasing to decreasing, or decreasing to increasing. So let's go back into second calc and let's find maximum. Again, it's all about creating a left bound, going to the left of your max, going to the right of your max. Enter. And this is a great thing to see because it's a big point of confusion for a lot of students. This x equals negative 1.269 e negative 6. Okay. Heads up, guys. If you ever see an e with a negative number associated with it, make sure you understand what the e means. E is times 10 to the power. Now let's think about what negative 1.269 times 10 to the negative 6 is. Well, if you multiply by 10 to the negative 6, you're dividing this number by 10 times. Whenever you divide by 10, you just can slide the decimal place over 6 times, creating 1, 2, 3, 4, 5 zeros before 1269. You need to be comfortable with seeing this and understanding that your calculator is really telling you you're talking about this 0.03. This negative 1.269 is really the location 0. It's just your calculator is using a numerical process, so sometimes it won't be dead on. Sometimes it'll be very close to. When it's very close to, you can assume with these problems that you can round your number and say, okay, my function is increasing from negative infinity to 0. Again, we look from left to right. We start from the left. My function is going up until 0. We will continue to go to the right towards positive infinity. We were doing the same thing for the previous one. So now I have to find the minimum. Second calc 3, go to the left of the min, go to the right of the min. Have your calculator guess. It's nice that they give you a whole number. They might be giving you like 1.999999. You can go ahead and assume in this class that it's at the whole number location 2. So my function goes down between 0 and 2. And then my function goes up after 2. So 2 to infinity. Cool. Cool. What is F? Positive and decreasing. Okay, well, we found the zeros were negative 0.879, 1.347, and 2.532. So those are important values. We see that we have a max at x equals 0. We have a min at x equals 2 using that. When are we positive and decreasing? Well, if we are positive between here and here and here and here, if we are decreasing between 0 and 2, we're going to have to go from 0 to 1.347. Let's double check. From 0 to this, from x equals 0 to x equals 1.347. Again, I have trace on, so it should see that interval. So 0 to 1.347. What is the rate of change of f positive and increasing? These are the tricky problems that we really struggle with. We change the question. We understand that we're talking about slopes. When slopes are positive, positive slopes, increasing. When slopes are increasing, 0, 1, 2, 3, 4, 5. Negative 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. We are concave up. That's one way to translate. Or you can say, hey, my slopes will be positive and increasing 1, 2, 3, 4, 5. If I have slopes of 1, 2, 3, 4, 5, I am going to be this shape, increasing concave up. Okay. So where am I increasing concave up? Well, right here when I get to the minimum, I start increasing. See, I can see I'm increasing concave down. I'm decreasing concave down to my point of inflection, decreasing concave up till my minimum, increasing concave up. So increasing concave up will be from my minimum at 2 to infinity. When is F decreasing? At a decreasing rate. Okay, so F is going down, but the rates are decreasing. If the slopes are decreasing, 5, 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4, negative 5. My graph must be concave down. So I need to be going down and concave down. Okay, let's think about if F is decreasing, the slopes have to be negative. Negative and decreasing, negative 1, negative 2, negative 3, negative 4, negative 5. Those are getting more negative. They're decreasing the values. Okay, so we are looking for decreasing concave down, a shape of that. So we are concave down until the point of inflection of 1. We hit the max at 0, and then we hit our point of inflection at 1. 0 to 1 is going to be my answer. What is the average rate of change from negative 1 to 4? Great. This is a situation where we need to calculate the slope between these 2 points. This is where I use my friend Mr. Trace. If I'm in trace, I can just find the 2 points. I got negative 1 is negative 1. Here's my first point right there. And then if I plug in 4, I get 19. Can't even see it, but it's there. What's the change in my y's? I went up 20. 19 minus negative 1, that's up 20. What's the change in my x's? I went over 5. It's good numbers, Mr. Huffaker. Mr. Huffaker, make this homework. We'd say on average, big F increases. It's a positive number. The slope is positive. 4 y's per x over the interval, negative 1 to 4. Find the horizontal distance between the relative max and the relative min. All right, well, the relative max is at 0. The relative min was at 2. So between 0 and 2, the horizontal distance is 2. Find the solutions to the equation f of x equals 1. This is why I like finding my zeros using y equals 0, because now we're comfortable with finding the solutions to the function equaling 1. We can just graph y equals 1 instead of y equals 0, and then find the intersection. Second calc intersect. We got 3. X equals negative 0.732. Second one. X equals 1. Last one. X equals 2.732. All right, there we go. That was the first question. Next question. The intensity of light coming out of a laser in a science experiment is modeled by 10.3 over x squared for x is greater than 1. Okay, so let's start over. 10.3 over x squared. If you like to use the fraction button, use it. That's alpha F1. Pops up fractions. I actually Used to hate the fraction button because when I had a graphing calculator, uh, they didn't have it. But now I see its use. It prevents mistakes typing things in with lots of parentheses. Um, Here's the first situation where a domain is present. We are told we are looking just to the right of 1. What I'm going to do is not just graph with a standard window. I'm going to adjust my window. I'm going to say, hey, let's start at 1. Maybe let's go from 1 to 10. Another thing I can do is utilize zoom fit. Zoom 0 is zoom fit. Now, what zoom fit does is the calculator takes the x's that you use in your window and it'll calculate the y's and just show you the graph perfectly in the window, in your X window that you decided to use. So I'm going to zoom fit and I can see the beautiful graph here. Okay. I like to use zoom fit a lot in my calculus class. It helps students see what they need to see. All right. First question is, what is the intensity of light? N is measured in candelas. This is a great time to press trace and just type in 3. Now you get 1.144. Just make sure you understand all I'm doing is plugging in 3 into the function 10.3 over 9. If I calculated 10.3 over 9, I would get 1.144. But your calculator does that quickly using trace. Typing in the number, it puts the input into the function. So we get 1.144 candelas. At what distance from the light is the intensity 5 candelas? So again, x is a distance. What we're trying to do is solve the equation 5 equals 10.3 over x squared. Now I can solve this by hand by multiplying both sides by x squared and dividing by 5 and then square rooting. But let's do both. Let's do the easy way, which is like, hey, I have a calculator. Let's go. Let's find the intersection with y equals 5. Y's represent candelas. X's represent centimeters. And I get 1.35, 435 centimeters. Let's go ahead and solve that equation. 5x squared equals 10.3. X squared equals... Oh, what's up, Huff? Hey, good homework. Good numbers on the first problem here. Do you want me to pause or? Okay. And we're back. So I'm solving this equation by hand. I'm going to square root 10.3 over 5. Watch how you can get the same answer. So it's just like good to be able to check, like, could I do this by hand? And like, wouldn't be able to get the answer, the numeric answer. But this would be like as simplified as possible. You go 1.435. Find the average rate of change between 1 to 3, 3 to 5, 5 to 7. Indicate units of measurement. So it's really important to understand like y's per x. Y's are candelas in here in this situation. Candelas per centimeter. Okay, so that's going to be the units if I divide the y's and the x's, y's per x. I mean, I feel like I can program something in really quickly. We don't want the graph. We don't want y equals 5 anymore because we are finding when x is 1, when x is 3. I can show you some tricks here. Oops. Make sure you press trace first. Click 1. We're going 1 to 3 first. Okay, so I got 10.3. If you find a location like that, it's usually stored in Y. See, like whenever you like find something on your graph, it gets stored. Now watch what happens when I press X. 1. Watch what I could do. If I wanted to, I'll show you just a little trick. You don't have to do this. This might be a little bit too advanced for you right now. You could say, hey, let's take that Y. I'm going to make that my Y1. So I'll make it B. Or I'll make it, yeah, I'll make it B. So this is B. And then we need to find 3, 1 to 3. I'm going to take that Y, make it A. So N of 3 was 1.144. Make that A. You can say B minus A over 2. Boom. Just calculated the average rate of change. Don't have to do that. If you guys want to simply do, I screwed that up. See, it should be A minus B over 2. Don't worry about this. We'll work on this later when we need to work on this. Instead, you should just be taking the Y2 minus the Y1. And what I like to do in my calculator is, if you have it, hold on to it so it's exact, minus the Y1. We don't like to put rounded answers in finding a new answer, divided by x2 minus x1. All right, on average, n decreases 4.577 candelas per centimeter over the interval 1 to 3. Let's find 5. Sorry, you have to press trace first. 5.412. If you want to store that as D, you could do that. You don't have to, though. I can do Y2 minus Y1 over 2. On average, N decreases 0.366 candelas per centimeter over the interval from 3 to 5. And let's finish off by finding 7. I can't even see the value. It's like 0.210. Well, again, once you find a trace, it's stored in your home screen as a Y. I can take that Y value, store it as E. 210. See, this is the example of don't use this rounded answer. Use this entire number to get the most accurate answer. Y2 minus Y1, again, over 2. Don't divide it by 2 yet because you're going to make a mistake in terms of order of operations. Do that. On average, N decreases 0.100 candelas per centimeter over the interval 5 to 7. This makes sense if you look at the graph. We are decreasing quicker at the beginning, and we are decreasing slower. Yep, I'll say that. Is N decreasing at an increasing or decreasing rate? Are the slopes increasing? If slopes are increasing, negative 3, 2, 1, 0, 1, 2, 3, 4, 5, we are concave up. If the slopes are decreasing, we are concave down. 5, 4, 3, 2, 1, 0, -1, -2, -3, -4, -5. Okay? It's not something I memorize. It's just like something I can think about, understand. Boom. No. Is this graph concave up or concave down? It's concave up. So the slopes or the rates are increasing. Based on its rates of change, could n be a quadratic function? So the rates of change need to be need to follow a pattern, a linear pattern. So like, let's look at the change in the rates, like the difference. 1 point, actually, 0.366 minus 4.577. Okay. 0.1 minus 0.366. I'd have to go further to check. I don't have enough. Like when you have two, we made that mistake on the practice problems. If you have two rates of change, you could think it's an exponential function, unless you were told it's a quadratic function. So why don't we find the rate of change between 7 and 9? F minus E over 2. Okay. So negative 4.211, negative 0.266, and then I got 0.1, sorry, 0.4, 0.04 minus 0.1. I got that value. Just gonna save the values in order. This is not like, you kind of know it's not a quadratic function, but it's like good to just double check. What were the changes? I'm I'm just gonna punt here. I don't want to like, I'm just gonna say no. There's not a linear pattern because there's not gonna be. We're just gonna say no. Don't stress out about this. We'll give you easier values to calculate. All right, cool. Let's keep going. This is becoming longer. These calculator questions take a lot of time to like get in and figure out. All right, so another equation, motion question. Let's just do our best to try to figure this out. It's not like last class's homework. We're talking about t's bigger than 0, so I'm going to start at 0. I'm going to zoom fit 0 to 10. All right. Okay. We have feet per second, motion, feet per second, velocity. Okay. If you find the average rate of change between 0, I keep messing up, press trace. This is what this stuff means. I start at a position of 0 feet at a time of 0 seconds. Press trace, go to 2. I get to a position of 10 after 2 seconds. 10 feet is my net change over 2 seconds. On average, the object increased its position by 5 feet per second. Y's per x. Y's per x are feet per second. On average, particles' position increases by 5 feet per second over the interval 0 to 2. Okay, this is like how quickly it is moving. Okay, from 4 to 5. Why is it I don't like that. What is it? Why is it doing that? Why isn't it? Can I just get I don't know why it's giving me a nice fraction. I don't like it, but whatever. From 4 to 5, we can see that um, the graph is decreasing. Okay. X of t is decreasing, which means the slopes are negative, which means the position is decreasing. A position that's higher to a position that's lower. How can you think of that in terms of motion? Well, if you are just moving to the right or to the left and your position is decreasing, we'd say this object is moving left. We don't talk about motion at all in our lesson. So if this is confusing to you, it's okay. It's not going to be on your quiz or on your test. It's just like stretching your physics brains. Object is furthest to the right when its position is at a maximum. We can find the maximum of my position. These positions, I mean, maybe it's important to kind of look at what this means. X is time, Y is position. I started at a position of 0. My position is increasing. We're talking about an object just moving to the right or to the left. If its position is increasing, it's moving to the right. If its position is decreasing, it's moving to the left. My object gets to a max position of 10.206 at around 2.5. This max position is when it's going to be furthest to the right, because when the position increases, it's going to the right. I want to make sure that was correct. I probably should look a little bit higher. Make sure you're way to the left and way to the right. Okay. X's stand for times. Y's stand for feet. Cool. After the object turned around and returns towards the origin, how long did it take for the object to move back to 6 feet from the origin? Okay, so this is when we're figuring out when our position equals 6. So it starts moving back towards the origin. When does it get to 6? Is at that time. This would have been a great time to actually store these values. So I'm going to go back and store them just because it's good to have them stored. Replace some of the values from the last problem. Left, right. Okay, this is stored as an X. x is now that value. Store that. That's now going to be my a value. And then my intersection, this is how I'm going to get the most accurate answers, providing use the entire decimal. That I'm going to store as b. That x value is now this. Store that as b. How much time transpires? Take your b, subtract your a. Took me 5.0878 or 0.88 seconds. From 10 to 20, I don't have a window from 10 to 20. So let's graph from 10 to 20. Let's just graph from 0 to 20. Let's zoom fit it. Let's zoom 0, zoom fit. Is my graph concave up or concave down? It looks like it's concave up. It's definitely concave up. You can look at your slopes if you wanted to over a bunch of intervals to confirm that, but we're going to just say it's concave up. Based on the concavity, is the rate of change increasing or decreasing? Interpret the meaning of the result in the context of the object's motion. Ooh. Okay, well, concave up means get your slopes out. 0, 1, 2, 3, 4, 5. Negative 5, 4, 3, 2, 1, 0. 1, 2, 3, 4, 5. Concave up means the slopes are increasing. In terms of the object's motion, we can say we are going left, but we're kind of slowing down going left. We're like decelerating. We are going slower to the left as we're traveling. It's tough to understand. I really wish we just kind of like hit motion hard. I do it in calculus. We have an entire unit just on motion, but it's not until the second semester. So we'll just do our best here. The position is decreasing. When my position's decreasing, I'm moving to the left. When my position's increasing, I'm moving to the right. Position's decreasing at an increasing rate. It's going to be slowing down. This is very much a calculus question. All right. We have a water fountain, okay? Like those dudes in the hallways where you could fill up your water bottle. When you put your water bottle in there, the stream coming out is consistent, okay? It's a consistent stream. So the volume that's entering your water bottle is consistent. What we're trying to do is look at how is the height or the depth in your water bottle changing, okay? And all you got to think of is the following. If you're wide, the wider you are, the more volume it's going to take to increase your depth. So if you're wide, your depth is increasing slowly. If you are narrow, when you fill up your water bottle, your little teeny tiny skinny water bottle, it's going to rise very quickly. Okay. So if we go wide to narrow, it will be increasing in a concave up manner because it'll be slow at the bottom and then it will get faster, increasing its depth towards the top. So concave up is like this way in terms of its depth. This would be like increasing very quickly but consistently. This would be increasing very slowly but consistently. This concave up, this would have to be concave down. The bottom would fill up very quickly, but as I get further and further up, the depth is going to slow down. This is concave down. Think about that while you're doing these. Like quick increase, constant depth, slow increase, constant depth. This would be concave down. That would be concave up. Hopefully it makes sense. The ink bottle, we are wide and consistent. Then we are going to be concave up because we are going from slower to faster in terms of depth. And then we are narrow and consistent, so fastly constant. So I would say ink bottle, slow and constant, concave up, and then continuing at that rate. So we got a straight line, a curve, and then continuing on that rate, a faster rate of depth change than the beginning. Slow, constant rate, concave, continuing on at that rate. Okay. The conical flask is just going to be straight concave up. We will be slowly increasing our depth. Then we will increase the rate. At the end, it looks like it's straight. So maybe we're going to like finish off with a little bit of a tiny segment that continues on at this rate. Boiling flask goes from concave up to concave down, like quick increase to slow, slow increase to quick. So I'm thinking concave up to concave down. Bucket, quicker increase to slower increase, concave down. Quicker increase to slower increase, concave down. Okay. Concave up. Slower to faster. I got to make sure I like this, the bucket. Faster to slower, concave down. Faster to slower, like increasing quicker, increasing slower. Your rates are decreasing. Conical flask, concave up, slower to quicker. It's like it gets crossed in your mind. If this is concave up, I'm going from slower increase to faster increase. I'm thinking this guy. That's my bottle. One of those like funky coffee mugs. Concave down. I'm going faster in terms of my increase to slower. A vase or something like that. Concave up to concave down. I go slow to fast. So like slow to fast, fast to slow. Slow to fast, fast to slow. Slow to fast, fast to slow. Constant but slow increase. Constant but fast increase. Oh. Slow to fast, fast to slow, slow to fast. It looks like it. Slow to fast, fast to slow, slow to fast. Funky water bottles. All right. Hope we understand this. Sorry about the motion problem. It's tricky to understand. This page and the previous page, I'd say, is more important into what your quiz is going to look like. Cool. All right. Messers out.